Tonight we're going to travel to the edge of everything, not a metaphor, not a poetic idea. The actual edge of what the human eye, aided by the most powerful instrument our civilization has ever constructed, can possibly see. And tonight, before you close your eyes, I want to take you there. I want to show you what sits at the furthest boundary of the observable universe, a galaxy, ancient beyond any number that feels real, so distant that the light you would need to detect it left its source when the universe was less than 300 million years old, before our sun existed, before our planet existed, before anything we call home had any right to exist at all. Here is what makes this terrifying. That light, those ancient photons that travelled for more than 13 billion years across the expanding fabric of space, arrived here, to us, to a small blue world orbiting an unremarkable star on the quiet outer arm of one of hundreds of billions of galaxies. They crossed a distance so incomprehensible that no analogy fully survives the attempt. And when our instruments finally caught them, barely a whisper above the noise of the cosmos, scientists stared at the data and felt something very close to vertigo, because what they found at the edge should not have been there. Not like that. Not that large. Not that bright. Not that soon after the beginning of everything. And that is what we are going to sit with tonight. The discovery, the distance, the silence that surrounds it, and the deeply unsettling, deeply beautiful truth that we, a species that only recently learned to fly, have somehow found the courage and the curiosity to look all the way back to the dawn of time itself and catch a glimpse of something that was already ancient before the Earth was born. Tonight, we're going to look further than any human being has ever looked before. Not in a spacecraft, not through some future technology that does not exist yet. Tonight, we're going to do it together, right here, in the quiet dark, before you sleep. We're going to travel to the very edge of the observable universe and visit the most distant object ever discovered by human science. And I promise you, by the time we arrive, the way you think about the night sky above your head will never be quite the same. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. I want you to do something for me. I want you to imagine standing outside tonight, wherever you are, and looking straight up. Maybe the sky's clear. Maybe you can see a handful of stars scattered across the dark above you, or maybe you can see hundreds of them, depending on where you live and how far you are from city lights. Either way, I want you to pick one, any one. A single point of light, steady and quiet, hanging there in the blackness as it has every night of your life. That light, that tiny, almost fragile-looking point is not arriving from somewhere nearby. It is not like the glow of a street lamp down the road or the beam of a passing plane. That light left its source years ago, decades ago, in some cases centuries or even thousands of years ago. You're not seeing the star as it is right now. You're seeing it as it was. You're looking into the past. That is the first thing I need you to hold on to tonight, because everything we're going to explore together rests on this single, beautiful and slightly unsettling idea. In space, distance, and time are the same thing. The further away something is, the further back in time you're looking when you observe it. The speed of light, though it is the fastest thing in the known universe, is not infinite. Light travels at roughly 186,000 miles per second. That is fast, almost unimaginably fast, but space is almost unimaginably large. And so, when you look out at the cosmos, you are never seeing the universe as it is right now. You're always, without exception, seeing the universe as it was. You are an archaeologist of light, reading the ancient record that photons carry across the void. This is not a flaw in our instruments or a limitation we might someday overcome. It is a fundamental feature of reality itself. Even looking at the sun, the star at the center of our own solar system, you are seeing it as it was roughly 8 minutes ago. The light touching your eyes right now left the surface of the sun 8 minutes before it reached you. If the sun were to simply vanish this instant, we would not know for 8 minutes. We would continue bathing in its light completely unaware. Now stretch that idea outward. Our nearest stellar neighbour, Proxima Centauri, sits about 4¼ light years away. When you look at it, you're seeing it as it was 4 years ago. The Andromeda Galaxy, the largest galaxy nearest to our own Milky Way, is about 2.5 million light-years away. When astronomers point their telescopes at it, they are receiving light that left Andromeda 2.5 million years ago, when our ancestors were still early humans walking the African savanna and had never once looked up at the stars with the kind of wondering minds we carry now. And yet, Andromeda is practically next door compared to where we are going tonight. The observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang, stretches roughly 46 billion light-years in every direction. That number is worth sitting with for a moment. 46 billion light-years. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second, every second for 365 days. And the observable universe extends 46 billion of those units in every direction, from where you're sitting right now. You're at the center of your own observable universe, and so is every other point in space. Because the universe has no center, no edge you could land on, no wall you could press your hand against. It is expanding in every direction simultaneously, and the horizon of what we can see is defined only by how far light has been able to travel since the beginning of time. Now, somewhere near that horizon, something was recently found. Something that has shaken cosmologists and astronomers and forced scientists to re-examine some of their most confident assumptions about how the universe works. An object so distant that the light we detected from it left its source when the universe was less than 300 million years old. To put that in perspective, the universe is currently about 13.8 billion years old. We are seeing this object as it existed when the universe was barely 2% of its current age. It is like finding a photograph of a person taken 2 days after they were born and realizing the face in that photograph belongs to someone who is now in their 50s. Except the distances involved are so vast, so numbingly enormous, that even the word vast does not do them justice. Here is the thing most people do not realize about this kind of discovery. It is not simply a matter of pointing a telescope in a direction and seeing further. The universe is not static and transparent and patiently waiting for us to look. Space itself is expanding. The light from the most distant objects is stretched by that expansion, pulled from the wavelengths of visible light down into infrared, into longer and longer waves that human eyes cannot see and that even many telescopes cannot detect. To find objects at the true edge of the observable universe requires instruments specifically designed to see in wavelengths far beyond visible light. It required decades of planning, an almost incomprehensible feat of engineering, and eventually the successful launch and deployment of the most powerful space telescope humanity has ever built. And even then, the signals we are looking for are barely there. They are whispers, echoes of light that began their journey before our planet existed, arriving at our detectors as the faintest possible trace of a universe in its infancy. That is what we found. And tonight, I am going to take you through the whole story. What we found, how we found it, why it shocked the people who spent their lives preparing to make exactly this kind of discovery, and what it means for everything we thought we understood about the cosmos. By the end of tonight, you are going to understand exactly why the most distant object ever discovered is not just a record in a database or a number in a scientific paper. It is a window that looks directly into the first light of the universe, and looking through it, if you let yourself really feel the scale of what you're seeing, is one of the most profound experiences a human mind can have. So settle in. Let the dark be comfortable around you. Let the weight of the day begin to lift, and let us go together, all the way to the edge of everything. There is something I want you to think about before we go any further. Something that sounds simple at first, but the longer you sit with it, the stranger and more beautiful it becomes. When you look at anything, you're not seeing it as it is right now. You are seeing it as it was. Every single act of seeing, every glance across a room, every look out a window, every moment you have ever spent gazing at the night sky, has been a small act of time travel. Light takes time to travel, and because it does, the image that forms in your eyes is always a picture of the past. Now, in everyday life, this barely matters. When you look at a friend sitting across a table from you, the light reflecting off their face takes such a tiny fraction of a second to reach your eyes that the delay is completely meaningless. You're seeing them as they were a billionth of a second ago, which is, for all practical purposes now. But as distances grow, the delay grows with them, and in the universe, distances grow to scale so extreme that the delay becomes the entire point. It becomes the most important thing about what you're looking at. It becomes the difference between seeing something as it is and seeing something as it was billions of years before you were born. Let me give you a ladder to climb, a series of steps, each one further than the last, so you can feel the idea building beneath you as we go. Start close. The Moon, our nearest companion in space, sits roughly 239,000 miles away on average. Light covers that distance in about 1.25 seconds. When you look at the Moon on a clear night, you're seeing it as it was just over a second ago. That is a delay so small it feels irrelevant, and yet it is real. The Moon you see is a memory, already gone by the time it reaches you. Now move further out. The Sun is about 93 million miles from Earth. Light takes roughly 8 minutes and 20 seconds to travel that distance. The sunlight warming your skin right now, the light that makes shadows and colours, and the blue of the daytime sky left the surface of the Sun 8 minutes ago. You have never, not once in your life, seen the Sun as it actually is at this moment. You have only ever seen where it was 8 minutes in the past. Step further out still. Mars, our neighbouring planet, sits anywhere from about 35 million to about 250 million miles away from us, depending on where both planets are in their orbits. At its closest, a signal travelling at the speed of light takes about 3 minutes to reach Mars. At its farthest, that same signal takes over 20 minutes. This is not just a philosophical curiosity. This is a real operational problem for space missions. When we sent rovers to Mars, every command sent from Earth arrived on Mars with a delay of several minutes, and every signal sent back took just as long to return. There is no such thing as real-time communication across interplanetary distances. The universe simply does not allow it. Now take one enormous step further. Leave the solar system entirely. Travel to the nearest star system beyond our Sun, a small cluster of stars called Alpha Centauri, located about 4.25 light years away. A light year, remember, is the distance light travels in 1 full year, and Alpha Centauri is 4.25 of those distances away from us. When astronomers observe Alpha Centauri, they are seeing those stars as they were 4.25 years ago. If something dramatic happened there, a large flare, a cataclysmic explosion, anything, we would not know about it for 4.25 years. We would be completely in the dark in every sense until that light finally reached us. And Alpha Centauri is our neighbour. In cosmic terms, it is practically in our backyard. Here is where the scale starts to become something more than just large. It starts to become something that changes how you feel about the sky above you. The Milky Way, our home galaxy, is roughly 100,000 light-years across. Some of the stars you can see with the naked eye on a clear night are thousands of light-years away. The light from those stars left their sources before recorded human history began, before the pyramids were built, before any civilization we know by name had learned to write down its stories. That light has been travelling through the void for all of human history, and only now, tonight, is it finally reaching your eyes. Think about that. Those photons have been crossing the galaxy since before anyone on Earth had ever looked up and wondered where they came from. Now step out further still, past the Milky Way entirely. The Andromeda Galaxy, our largest galactic neighbour, is approximately 2.5 million light-years away. When you look at Andromeda, even just as a faint smudge visible to the naked eye under dark skies, you're seeing it as it was 2.5 million years ago. Our species, Homo sapiens, did not yet exist when that light began its journey. The ancestors walking the Earth, when those photons departed Andromeda, were early members of the genus Homo, or possibly even earlier hominids, creatures who would not have recognized a telescope or a question about galaxies. And yet the light from that ancient snapshot of Andromeda has travelled all that time, all that distance, and arrived precisely at your eyes, on this night, as you lie here listening. This is the framework that makes everything else we're going to talk about tonight not just intellectually interesting, but emotionally staggering. Because the object we're ultimately going to reach, the most distant thing ever detected by human instruments, is not millions of light-years away. It is not even a few billion light-years away. It sits at a distance so extreme that the light we captured from it left its source when the universe itself was only a few 100 million years old. We are talking about light that has been travelling for more than 13 billion years. light that began its journey in a universe so young, so different from the one we know, that the very physics of what existed then would be almost unrecognizable to us now. Here is the thing most people do not realize when they first encounter this idea. When we say we are seeing something far away, we are not just describing a location in space, we are describing a location in time. The two are inseparable. You cannot look at something 13 billion light-years away and see it as it is today. It is physically impossible. The light that shows you what that object looks like today has not even finished travelling yet. It will not arrive here for billions of years. What we see, what we detect, what we study and measure and argue about in scientific papers is always and only the past. The deep past, in some cases the ancient past. In the case of the most distant object ever found, a past so remote it sits closer to the moment of creation than to the present day. So when I tell you, as we continue tonight, that we found something at the edge of the observable universe, I want you to feel both of those words equally, the edge of space and the edge of time, because they are the same edge, and we have reached it. There is a horizon around you right now, not the one you can see when you look out at a landscape, where the ground curves away and disappears from view. This one is invisible, and it surrounds you in every direction, above and below, left and right, in front and behind. It is called the cosmic horizon, or the edge of the observable universe, and it is one of the strangest and most consequential facts about the reality we inhabit. Beyond it, there is almost certainly more universe, possibly vastly more, possibly infinite more, but we cannot see it, cannot detect it, cannot reach it with any signal or instrument we have or could ever build. It is permanently, irrevocably hidden from us. And tonight, we are going to stand as close to that horizon as human science has ever managed to get. To understand why the horizon exists, you need to hold two ideas at once. The first is the one we spent time with in the last chapter. Light travels at a fixed speed and therefore takes time to cross any distance. The second idea is this: the universe has not existed forever. It began. Roughly 13.8 billion years ago, in an event we call the Big Bang, all of space, all of time, all of matter and energy erupted into existence from an unimaginably hot and dense state, and began expanding outward in every direction simultaneously. That expansion has never stopped. It has been happening every moment since the beginning, and it is happening right now as you listen to this. Space itself is growing, stretching, carrying galaxies away from each other like dots drawn on the surface of a balloon being slowly inflated. Now put those two ideas together. If the universe began 13.8 billion years ago, and light travels at a fixed speed, then the furthest light we could possibly receive right now is light that has been travelling for 13.8 billion years. That sets a hard limit on what we can observe. No matter how powerful our telescopes become, no matter how sensitive our instruments grow, we can never see anything from which light has not yet had enough time to reach us. That boundary, the furthest distance from which light could have travelled since the beginning of time, defines the edge of our observable universe. It is not a wall. It is not a place where space ends. It is simply the limit of our cosmic vision, drawn in light and time. But here is where it gets stranger, and this is the part that genuinely unsettles people when they first encounter it. The observable universe is not 13.8 billion light-years in radius. You might expect it to be. If light has been travelling for 13.8 billion years, surely the furthest it could have gone is 13.8 billion light-years. But that calculation ignores the expansion of space itself. While light was travelling toward us, the universe was expanding. The source of that ancient light was being carried further and further away by the stretching of space even as its photons were crossing the void toward us. When you account for all of that expansion, the actual distance to the edge of the observable universe today is roughly 46 billion light-years in every direction. The universe is, in a meaningful sense, much larger than the amount of time it has existed would naively suggest. Space does not have a speed limit. Only light does. This means our observable universe, the sphere of everything we can in principle detect and study, spans a diameter of about 93 billion light-years. That is the size of our cosmic window. Everything outside that window is beyond reach, not because of any failure of technology or imagination, but because of the hard geometry of time and light. Signals from those regions have simply not had enough time to reach us yet. And because the universe is expanding, and because the most distant regions are receding from us faster than light can cross the growing gap, some of those signals will never reach us. The regions beyond our horizon are not just currently invisible. For many of them, they are permanently invisible. They are lost to us by the laws of physics themselves. Now consider what that means for a moment. We live inside a bubble of knowable space. Everything we have ever observed, every star, every galaxy, every nebula, every quasar, every ancient signal, captured by our most powerful instruments, sits inside this bubble, and outside it, in every direction, there is almost certainly more. The leading models of cosmology suggest that the universe extends far beyond our observable horizon. Some models suggest it extends infinitely. If those models are correct, then what we can see is not just small compared to the whole, it is infinitesimally small. A grain of sand on a beach that goes on forever. The part of the universe we will ever know is a rounding error compared to what actually exists. That thought is one of the most quietly terrifying things I know. Here is the thing most people do not realize about our cosmic horizon. It is not the same for everyone, and it is not fixed in time. A civilization on a planet in a distant galaxy has its own observable universe, its own bubble of knowable space centered on them. Some of their bubble overlaps with ours. Some of it extends in directions we can never see. Every point in the universe is the center of its own observable cosmos, surrounded by its own horizon, looking out at its own unique slice of the whole. There is no single privileged view, no master vantage point from which the entire universe can be seen at once. We are all, every civilization that has ever or will ever exist anywhere in the cosmos, looking out from inside our own private bubble of light and time, and the horizon is not static. As time passes, light from more distant regions continues to arrive, and our observable universe slowly, very slowly, grows. But it grows more slowly than the expansion of space is pushing things beyond our reach. The net effect over cosmic timescales is that our observable universe will actually shrink relative to the total. Galaxies that are currently just barely within our observable range will eventually recede beyond our horizon as the expansion of space accelerates. In the far future, a civilization in our galaxy would look out at a universe that appears nearly empty, with almost no other galaxies visible, because all the others will have been carried beyond their horizon by the relentless expansion of space. The loneliness of that future cosmos is something I find genuinely moving to consider. But we are not in that future. We are here, now, at a remarkable moment in cosmic history when the universe is still young enough and our horizon still wide enough that we can see billions of galaxies spread across billions of light years in every direction. And at the very edge of that view, right up against the boundary where light and time conspire to draw our horizon, we have found something, a faint signal, an ancient light, the echo of a galaxy so distant that it sits not just near the edge of our observable universe, but near the edge of time itself, back when the cosmos was barely beginning to fill with the first structures it would ever form. That is where we are heading, to the very edge of what we can see, to the horizon itself. Every time humanity has built a better eye, the universe has revealed something we did not expect. That is not a coincidence. It is a pattern that has repeated itself across centuries of astronomy, from the first crude lenses pointed at the night sky to the extraordinary machines we have placed in orbit around our planet. Every leap in our ability to see has been followed immediately by a leap in our understanding, and more often than not, that new understanding has made the universe seem stranger, larger, and more mysterious than it appeared before. Tonight I want to take you through that journey, because you cannot fully appreciate what we found at the edge of everything without understanding the remarkable chain of human ingenuity that made it possible to look that far at all. The story begins, as so many stories in science do, with someone deciding to point something at the sky and pay close attention to what they saw. In the early 1600s, an Italian scientist named Galileo Galilei turned a small refracting telescope toward the heavens and saw things no human being had ever seen before. He saw the moons of Jupiter circling their planet. He saw the phases of Venus. He saw that the Milky Way, that soft band of light arching across the night sky, was not a cloud or a mist, but a dense gathering of individual stars, so numerous and so close together that they blurred into a single glow when viewed with the naked eye. The universe, in the span of a few nights of observation, became suddenly and irreversibly larger than anyone had imagined. That telescope had a lens only a few centimetres across. It was by any modern standard a primitive instrument, and yet it shattered the boundaries of the known cosmos in a matter of weeks. For the next 3 centuries, astronomers built bigger and better telescopes, grinding ever larger mirrors and lenses, constructing towering observatories on mountain peaks, where the air was thin and the skies were dark and the seeing was steady. Each new instrument pushed the frontier a little further. In the early 20th century, an American astronomer named Edwin Hubble used the most powerful telescope of his era, mounted on Mount Wilson in California, to make one of the most consequential discoveries in the history of human thought. Those faint, fuzzy smudges scattered across the sky that some astronomers had called nebulae, assuming they were simply clouds of gas within our own galaxy, were not in our galaxy at all. They were entire galaxies in their own right, each one containing hundreds of billions of stars, each one sitting at distances so vast they made the Milky Way seem like a small neighbourhood on a very large planet. The universe was not one galaxy. It was billions of galaxies, and it was expanding, growing larger every moment, carrying those galaxies away from each other at speeds that increased with distance. But even the most powerful ground-based telescopes faced a fundamental problem that no amount of engineering could fully solve: Earth's atmosphere. The same thin layer of air that makes our planet habitable also makes it a terrible place to do deep astronomy. Air is not perfectly clear. It shimmers and trembles with temperature variations, blurring the images that reach our telescopes and washing out the faintest signals from the most distant sources. It also absorbs certain wavelengths of light almost entirely, blocking infrared radiation, ultraviolet light, and many other parts of the electromagnetic spectrum from ever reaching our instruments on the ground. To truly see the universe in all its frequencies and at its greatest depths, we needed to get above the atmosphere entirely. We needed to put a telescope in space. The Hubble Space Telescope, launched in April of 1990, was the fulfillment of that dream. Placed in orbit about 340 miles above Earth's surface, above virtually all of the atmosphere's blurring and absorbing effects, Hubble could see with a clarity and sharpness that no ground-based telescope could match. Its early images, once a flaw in its mirror was corrected by a dramatic repair mission in 1993, were revelatory. In one of its most famous observations, astronomers pointed Hubble at a tiny patch of sky in the constellation Ursa Major, a region that appeared completely empty to any previous instrument. They kept the telescope trained on that seemingly blank patch for 10 consecutive days, letting light accumulate on its detectors. What emerged from that long exposure, known as the Hubble Deep Field, was one of the most extraordinary images in the history of science. That tiny, apparently empty patch of sky contained nearly 3,000 galaxies, each one a vast island universe of billions of stars, stretching back to distances of billions of light years. The universe was not just large, it was almost incomprehensibly full. Hubble pushed the distance record for observed objects further and further back over the decades of its operation. It captured galaxies more than 13 billion light-years away, objects so ancient and so distant that they appeared as only a handful of pixels in its images, faint red smudges barely distinguishable from noise. But Hubble had limits. Its mirror, while large for a space telescope, was only 2.4 meters across. And more critically, Hubble saw primarily invisible light and ultraviolet wavelengths. The most distant objects in the universe, the ones nearest the cosmic horizon, have their light stretched by the expansion of space into infrared wavelengths, frequencies far redder than anything the human eye can detect. To see those objects, to push past Hubble's frontier and look into the first few 100 million years of cosmic history, we needed something fundamentally different. We needed a telescope designed from the ground up to see the infrared universe. That telescope took decades to design, fund, build, and launch. Its development was plagued by delays, cost overruns, and technical challenges so daunting that at various points it seemed the project might never be completed. But on the 25th of December, 2021, a rocket lifted off from a launch site in South America, carrying the most complex and expensive scientific instrument ever constructed by human hands. The James Webb Space Telescope, named after a former administrator of NASA, unfolded itself over the following weeks in a sequence of deployments so intricate and so critical that engineers described it as having 244 single points of failure, any one of which could have ended the mission. Every step worked. Every mechanism deployed correctly. The telescope reached its destination, a point in space about 1 million miles from Earth, and began cooling its instruments to temperatures just a few degrees above absolute zero, the coldest cold that physics permits, so that its own heat would not drown out the faint infrared signals it was designed to detect. When Webb began sending back its first images in the summer of 2022, the scientific community was, in the most literal sense, not prepared for what it saw. Galaxies sharper and more detailed than Hubble had ever shown. Stellar nurseries revealed in unprecedented clarity. And most relevant to everything we are discussing tonight, objects at distances so extreme that they shattered previous records almost immediately. Webb was not just a better version of Hubble. It was a different kind of instrument entirely, one capable of looking further back in time than anything that had come before it. And what it found at those unprecedented distances is what we are going to spend the rest of tonight exploring together. There is something deeply human about the desire to find the furthest thing, to push the boundary one step further than it has ever been pushed before, to stand at the edge of what is known and lean out just a little further into the unknown. Astronomers are, in this sense, no different from explorers or mountaineers or deep-sea divers. They are drawn to the frontier not simply because the science demands it, but because something in the human spirit cannot rest while there is still more to find. The history of the distance record in astronomy is the history of that restlessness, played out across decades of discovery, each breakthrough more staggering than the last, each new frontier dissolving almost as soon as it was reached. To understand how we arrived at the most distant object ever discovered, you need to understand the tool that made the journey possible. That tool is called redshift, and it is the ruler astronomers use to measure distances so vast that no other method can reach them. Here is how it works. Light, as you may know, travels in waves, and different wavelengths of light correspond to different colours. Visible light spans from violet at the short wavelength end to red at the long wavelength end, with all the colours of the rainbow arranged between them. When a source of light is moving away from you, those waves get stretched out. The wavelengths become longer. The light shifts toward the red end of the spectrum. This is called redshift, and it is the cosmic equivalent of the way a siren sounds lower in pitch as an ambulance drives away from you. The faster something is moving away, the more its light is redshifted. And in an expanding universe where the most distant galaxies are receding from us fastest, the most distant objects show the highest redshifts. By measuring how redshifted an object's light is, astronomers can calculate how fast it is receding, how far away it is, and how long ago the light left its source. Redshift is not just a measurement, it is a time machine. The story of distance records begins in earnest in the 1960s, with the discovery of objects called quasars. Short for quasi-stellar radio sources, quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes consuming enormous quantities of matter. They blaze with the light of trillions of suns, making them visible across distances that would render ordinary galaxies invisible. When astronomers first began measuring their redshifts, the numbers were shocking. These objects were not sitting within our galaxy, or even in our immediate cosmic neighbourhood. They were billions of light-years away, receding at significant fractions of the speed of light, their light ancient beyond anything previously detected. The first quasars discovered with high redshifts pushed the frontier of known cosmic distances further than any previous observation. They were the first proof that our instruments could reach back in time not just millions of years, but billions of years into the history of the universe. Over the following decades, the record kept moving. Each new generation of telescopes found objects at greater distances and higher redshifts than the last. Astronomers developed a shorthand notation for redshift, labeling it with the letter Z. A redshift of 0 means no recession at all, an object sitting essentially still relative to us. A redshift of 1 means the light has been stretched to twice its original wavelength. Higher values of Z correspond to greater distances and earlier times in cosmic history. In the 1970s and 80s, redshift records crept up through values of 2 and 3, pushing observations back to when the universe was a few billion years old. In the 90s, as new spectrographs and more sensitive detectors came online, records climbed through 4 and 5. Each new value of Z was a step further back in time, a step closer to the beginning of everything. The Hubble Space Telescope, once its mirror was corrected and its instruments upgraded through a series of servicing missions, became the primary engine of this record-breaking era. The Hubble Deep Field images of the mid-90s revealed galaxies at redshifts of 4, 5, and beyond. Objects so distant their light had been travelling for more than 12 billion years before entering Hubble's mirror. Astronomers stared at those images with a combination of scientific excitement and something harder to name, a kind of vertigo that comes from realizing you're looking at a universe so young it barely resembles the one we inhabit today. The galaxies in those deep field images were not the elegant spirals and ellipticals we see in our cosmic neighborhood. They were small, irregular, lumpy, chaotic, infant structures still figuring out what they would eventually become. As the 2000s progressed, the record climbed higher still. Redshift 6, 7, 8. Each increment corresponded to looking back to when the universe was younger and younger, smaller and smaller, hotter and denser. At a redshift of 6, we are seeing the universe as it was about 900 million years old. At a redshift of 8, we reach back to when the universe was only about 600 million years old. At a redshift of 10, we approach the era when the very first stars and galaxies were switching on for the first time, flooding a previously dark universe with the first light it had ever known. Astronomers called this era the Cosmic Dawn, and reaching it observationally became one of the defining ambitions of the field: to see the first light, to witness the universe waking up. That was the goal, and every record-breaking discovery was one step closer to it. But there was a problem. As redshift values climbed above 6 or 7, the light from these distant objects shifted almost entirely out of the visible spectrum and into the infrared. Hubble, magnificent as it was, could only see a limited range of infrared wavelengths. The most ancient galaxies, the ones sitting at the highest redshifts, were becoming invisible to it. Their light was there, arriving at our corner of the universe after its long journey, but Hubble simply could not detect it efficiently. Ground-based infrared telescopes could push a little further, and some remarkable discoveries were made in this way. But the atmosphere remained a persistent obstacle, absorbing infrared wavelengths and adding noise that made the faintest signals nearly impossible to extract cleanly. The field was straining against a barrier that existing technology could not break through. The record as it stood before the James Webb Space Telescope began operations sat at a confirmed redshift of around 13, an object detected in Hubble imaging and confirmed with ground-based spectroscopy. That corresponded to seeing the universe as it was roughly 320 million years after the Big Bang, a blink of cosmic time after the beginning of everything. It was an extraordinary achievement, the product of decades of instrument development, observational skill and scientific determination. And yet, everyone in the field knew it was almost certainly not the true limit. The most distant objects were simply waiting beyond the range of existing instruments, their ancient light arriving undetected at our corner of the universe, patient and unknowing, carrying information about the earliest chapter of cosmic history that no human had yet found the means to read. That was about to change. Before we can truly appreciate what was found at the edge of the observable universe, we need to travel back. Not just in distance, not just in the abstract numbers of light years and redshift values, but in imagination. We need to try to picture what the universe actually looked like in those first few 100 million years after the Big Bang, when the objects we are discussing were first taking shape, because the universe of that era was so profoundly different from the one we inhabit today that calling it by the same name almost feels like a category error. It was younger, hotter, denser, darker in some ways and blazingly bright in others, and it was in the process of doing something it had never done before and would never do again. It was forming its very first structures, the first stars, the first galaxies, the first concentrations of matter massive enough to hold themselves together against the chaos of the surrounding cosmos. To understand how we got to that point, we need to start just a little earlier. In the first moments after the Big Bang, the universe was unimaginably hot. We are talking about temperatures measured in the billions and trillions of degrees, so extreme that matter as we know it could not exist. There were no atoms, no molecules, no stars, no anything we would recognize. There was only a seething, expanding plasma of fundamental particles, protons and neutrons and electrons and photons, all crammed together so tightly and moving so violently that they formed an opaque, glowing fog. Light could not travel freely through this fog. It was constantly being absorbed and re-emitted, trapped inside the plasma like sunlight inside a very thick cloud. For roughly 380,000 years after the Big Bang, the universe was essentially a bright, hot, opaque wall in every direction. Then something remarkable happened. As the universe expanded, it cooled, and when the temperature dropped to a few thousand degrees, something crossed a critical threshold. Electrons, which had until that point been moving too fast to be captured by protons, suddenly slowed down enough to be held. Atoms formed for the first time, hydrogen atoms mostly, the simplest possible atom, a single proton with a single electron orbiting it, snapping into existence across the entire universe in a cosmic instant. And when that happened, the fog cleared. Photons that had been trapped inside the plasma were suddenly free to travel. Light flooded the universe for the first time. That ancient light stretched by 13.8 billion years of cosmic expansion into the microwave range of the spectrum is what we call the cosmic microwave background, and we can still detect it today as a faint glow of radiation coming equally from every direction in the sky. It is the oldest light in the universe, a photograph of the cosmos when it was just 380,000 years old. But after that moment of clearing, the universe entered a period that astronomers call the cosmic dark ages. The newly formed hydrogen atoms scattered across the expanding cosmos, and for a very long time, hundreds of millions of years, there was nothing to light them up. No stars, no galaxies, no sources of radiation, just darkness. An enormous, expanding, silent darkness filled with clouds of hydrogen and helium, slowly drifting and clumping under the gentle pull of gravity. This era is one of the most difficult to study precisely because there was no light. You cannot observe darkness with a telescope. You can only infer what was happening from the physics of the situation and from the structures that emerged on the other side of it. What was happening during those dark ages was quiet but consequential. Gravity, patient and relentless, was doing its work. The hydrogen clouds were not perfectly uniform. There were tiny variations in density seeded by quantum fluctuations in the earliest moments of the Big Bang, regions that were ever so slightly denser than their surroundings. Those denser regions pulled in more matter, and as they grew denser, they pulled harder, attracting more material from their surroundings, collapsing inward under their own gravity over millions and then hundreds of millions of years. Inside those collapsing clouds, something extraordinary was building. Pressure, heat, density high enough that the nuclei of hydrogen atoms began fusing together, releasing energy. The first stars were igniting in the darkness. Those first stars were almost certainly nothing like the stars we see today. The universe at that point contained only hydrogen and helium, the two elements forged in the Big Bang. There were no heavier elements yet. No carbon, no oxygen, no iron, no silicon. All of that would eventually be created inside stars and scattered by their deaths. But in those early moments, working only with the lightest ingredients, the first stars that formed were likely enormous. Some models suggest they may have been hundreds or even thousands of times more massive than our Sun, blazing with ferocious intensity, burning through their fuel in just a few million years before exploding as supernovae and scattering the first heavy elements into the surrounding cosmos. They were brief, violent, and transformative. Their ultraviolet radiation began ionizing the hydrogen gas around them, slowly eating away at the neutral fog that had persisted since the Dark Ages, in a process called reionization that gradually made the universe transparent to ultraviolet light. And around these first stars, and around the dense knots of dark matter that gravity was assembling on larger scales, the first galaxies began to take shape. These were not the majestic spiral galaxies we see in the nearby universe, not the grand, pinwheeling structures with graceful arms of stars and glowing nebulae. They were small and irregular and chaotic, more like dense clusters of young stars embedded in clouds of gas than anything we would today call a galaxy by appearance. But they were real. They were gravitationally bound collections of stars, the first of their kind in the history of the universe. and they were doing something ancient and important, growing, merging with each other, consuming gas, forming new stars at extraordinary rates, building themselves into the larger structures that would eventually populate the cosmos we see around us today. This is the universe we are looking into when we point the James Webb Space Telescope at its highest redshift targets. We are not seeing the mature, settled universe of today. We are seeing the construction site, the moment of becoming, a cosmos still figuring out what it wants to be, with young galaxies blazing ferociously against a background of gas and dark matter and slowly clearing fog. And somewhere in that construction site, at a distance and a redshift so extreme that it pushes right up against the limits of what our instruments can detect, sits the object we're here to discuss tonight. A galaxy so ancient, so far away, and so surprisingly large that when astronomers finally confirmed what they were looking at, it forced them to ask a question that still does not have a fully satisfying answer. How did something like this exist so early? How was there already so much when there had been so little time? The year was 2024. The James Webb Space Telescope had been operational for roughly 2 years, and in that short time it had already rewritten entire sections of our understanding of the early universe. Record after record had fallen. Objects at redshifts of 11, 12, 13 had been identified in Webb's imaging data, each one pushing the frontier a little further back toward the cosmic dawn. The scientific community was in a state of sustained, almost breathless excitement, the kind that comes when a new instrument is performing so far beyond expectation that every week brings something no one has seen before. Astronomers around the world were sifting through Webb's data with the focused intensity of people who know they are living through a historic moment in their field. And then, from a survey program called JADES, the James Webb Advanced Deep Extragalactic Survey, something emerged from the data that stopped people in their tracks. JADES was not a spontaneous observation. It was the result of years of planning by an international team of astronomers who had secured hundreds of hours of Webb telescope time specifically to probe the deepest, most distant reaches of the observable universe. They chose their target fields carefully, regions of sky with relatively low interference from our own galaxy, where Webb's infrared detectors could stare into the ancient past with minimal obstruction. The survey combined 2 of Webb's most powerful instruments, its near-infrared camera, which could capture extraordinarily faint light across a range of infrared wavelengths, and its near-infrared spectrograph, which could spread that light into its component wavelengths and measure redshifts with precision. Together, these instruments allowed the team to not just detect distant objects but confirm exactly how distant they were, something previous surveys had often struggled to do reliably. In the imaging data from one of the JADES fields, a small smudge of light appeared that immediately attracted attention. It was faint, extremely faint, detectable only because Webb's mirror, 6.5 meters across and exquisitely sensitive, had been gathering its light for many hours of accumulated exposure time, but it was there. And when the team analysed the colours of the light coming from this object, the way its brightness varied across different infrared wavelengths, they noticed something that made their pulse quicken. The object showed a very sharp cutoff in its brightness at a specific wavelength. Below that wavelength, almost no light at all. Above it, a detectable signal. This pattern, called the Lyman break, is a telltale signature of extreme distance. It occurs because neutral hydrogen gas, which fills the space between galaxies in the early universe, absorbs light below a certain wavelength with almost perfect efficiency. The location of that cutoff in the spectrum tells you the redshift of the object, and in this case the cutoff was sitting at a wavelength that pointed to a redshift unlike anything previously confirmed. The team knew immediately that they needed spectroscopic confirmation. Identifying a Lyman break in imaging data is a strong indicator of high redshift, but it is not proof. False positives exist. Unusual dust, unusual stellar populations, unusual physical conditions can sometimes mimic the appearance of extreme distance in imaging alone. To confirm the redshift, they needed to use Webb's spectrograph to spread the object's faint light into its full spectrum and look for the detailed features that would uniquely pin down its distance. This is a painstaking process. The object was so distant and so faint that obtaining a usable spectrum required pointing Webb at it for an extended period, and then carefully extracting the signal from the noise. But when the spectroscopic data came in and the team sat down to analyse it, What they saw removed all doubt. The redshift of this object was 14.32. Let that number settle for a moment. A redshift of 14.32. To put that in the framework we have been building together tonight, this means the light from this galaxy left its source when the universe was approximately 290 million years old, not 290 million years before the present. 290 million years after the Big Bang itself. The universe today is 13.8 billion years old. This galaxy's light comes from a time when the universe was barely 2% of its current age. It is as if you were looking at a photograph of a person taken 48 hours after they were born, and that person is now 70 years old. Except the timescales involved are not decades but billions of years, and the object in the photograph is not a person, but an entire galaxy containing hundreds of millions of stars. The object was designated JADES GSSZ 14-0. The name is technical and dry, the kind of label that science attaches to discoveries to keep them organized in databases and papers. But behind that label sits something extraordinary. The most distant object ever confirmed by spectroscopic observation in the history of human astronomy. A galaxy sitting at the very edge of what we can see, its light a message sent before our solar system existed, before Earth existed, before any of the heavier elements that make up your body and mine had even been forged inside stellar furnaces. When that light began its journey, the universe was a very young and very different place, and it has been crossing the void ever since, for more than 13.5 billion years, until it arrived at the mirror of a telescope built by a species that would not appear on one of the cosmos's planets for another 4 billion years after that light departed. When the results were submitted for publication, and the broader astronomical community had a chance to examine the data, the reaction was a mixture of awe and scientific agitation. Awe, because breaking the distance record by such a significant margin was genuinely historic, the kind of result that will appear in astronomy textbooks for generations, and agitation, because the properties of this galaxy were deeply puzzling in ways that went beyond its extreme distance. It was not just far away, it was wrong, in the most scientifically interesting sense of that word. It had properties that our best models of galaxy formation did not predict should be possible at that epoch of the universe. It was too bright, it showed signs of being too massive, and it displayed evidence of chemical enrichment, the presence of heavier elements that implied it had already been forming stars for some time before this snapshot of it was taken. At 290 million years after the Big Bang, this galaxy appeared to have already lived a significant portion of a life that our models suggested it should barely have begun. That tension between observation and theory is where the real story begins, because finding the most distant object ever seen is remarkable enough on its own, but finding one that simultaneously challenges the foundations of our best cosmological models is something else entirely. It is the kind of discovery that does not just add a data point to a graph, it bends the graph. It forces scientists back to the drawing board, back to their equations and their simulations, to ask whether something fundamental about their picture of the early universe might need to be revised. And that question, still actively debated among the world's leading cosmologists, is one of the most exciting and unsettling open questions in all of modern science. There are numbers in astronomy that resist comprehension, not because they are complicated or require advanced mathematics to work with, but because the human mind was simply not built to feel them. We evolved on a small planet, moving at walking pace through landscapes measured in miles and kilometers. Our intuitions about size and distance are calibrated to that world. A mile feels like something. 100 miles is a long drive. 1,000 miles is a flight across a continent. Beyond that, the numbers begin to lose their emotional weight. They become abstract. They become, in a very real psychological sense, the same. 1,000,000 miles and 1,000,000,000,000 miles feel roughly equally incomprehensible to most people, even though one is 1,000,000 times larger than the other. Tonight I want to try something difficult. I want to try to make the distance to JADES GSZ 14-0 feel real. Not just intellectually acknowledged, but genuinely felt, at least for a moment, before it slips back into abstraction. Let us start with the light travel time, because that is the most direct way to approach the number. The light we detected from this galaxy left its source approximately 13.4 billion years ago. That is the time it has been travelling. 13.4 billion years. A year is 365 days. A day is 24 hours, an hour is 3,600 seconds. Multiply all of that out, and a year contains about 31 million seconds. Multiply that by 13.4 billion, and you get a number so large that even writing it out takes a long time. The light that entered Webb's mirror had been travelling for more than 420 quadrillion seconds. 420 followed by 15 zeros. Every single one of those seconds, that light was crossing the void at 186,000 miles per second. It never stopped. It never slowed. It crossed the expanding universe in an uninterrupted straight line for longer than any timescale that has any meaning in human experience. Let me try a different angle. Human civilization, as we generally measure it, is roughly 10,000 years old. That's when we began farming, building permanent settlements, developing writing and mathematics, and the first stirrings of what we call culture. 10,000 years feels like a very long time when you consider how much has happened in it. From the first clay tablets to the printing press, from the first bronze tools to the space telescope, 10,000 years of human history compressed into a single unit. Now, take that unit and stack it. Stack one 10,000-year human civilization on top of another, over and over again. How many do you need to stack before you reach 13.4 billion years? 1,340,000 civilizations worth of time. If every human civilization that has ever existed ran its full course, rose and fell, and was replaced by the next, and you lined them all up end to end, you would need more than 1 million of them to span the time that light from this galaxy has been travelling. Now let us try the distance itself, because light travel time, as staggering as it is, does not capture the full picture. Due to the expansion of space during the time that light was travelling, the galaxy that emitted it is now much further away than 13.4 billion light-years. The actual current distance to JD's GSZ 14-0 is estimated at around 33 to 35 billion light-years. A light-year is about 5.9 trillion miles. Multiply 5.9 trillion by 33 billion, and you get a current distance of roughly 195 sextillion miles. That is 195 followed by 21 zeros. If you tried to drive that distance in a car at highway speed, the journey would take longer than the current age of the universe by an almost incomprehensible factor. The number is so large it becomes paradoxically almost calming. It is so far beyond the reach of any human experience that it ceases to produce anxiety, and begins instead to produce a kind of quiet wonder. Here is another way to feel the scale. The fastest human-made object ever launched is the Parker Solar Probe, which at its closest approach to the Sun reaches speeds of about 430,000 miles per hour. That is extraordinary by any human standard. It is far faster than any vehicle a human being has ever travelled in. At that speed, you could circle the Earth in just over 3.5 minutes. You could reach the Moon in about 33 minutes. You could reach the Sun in about 9 days. At that speed, travelling continuously without stopping or slowing, you would reach the nearest star, Proxima Centauri, in roughly 6,800 years. To reach the galaxy we are discussing tonight at that same speed would take approximately 54 billion years. The universe is only 13.8 billion years old. You would need to wait for nearly 4 entire lifetimes of the current universe to complete the journey, assuming the destination were not moving further away with every passing moment due to cosmic expansion, which it is. I want to pause here, because I think this is a moment worth sitting inside for a few breaths. The light we caught from this galaxy has been travelling since before our solar system existed, before the Sun ignited, before the Earth formed from the disk of gas and rock surrounding that young star, before the first oceans appeared on Earth's surface, before the first single-celled organisms appeared in those oceans, before multicellular life, before plants, before animals, before the extinction of the dinosaurs, before the emergence of primates, before the first humans walked the savannah, before every civilization, every empire, every discovery, every war, every moment of joy or grief or love that has ever occurred on this planet. All of that, the entire history of our world and everything on it, happened after this light began its journey and before it arrived at our telescope. Every page of every history book ever written fits inside the final fraction of a second of that light's travel time, relatively speaking. Here is the thing most people do not realize when they first confront numbers like these. The distance to this galaxy is not just large in the way that a very big room is large, or even in the way that a continent is large. It is large in a way that puts it permanently and absolutely beyond any physical reach. There is no propulsion system, no theoretical engine, no exotic physics we have even imagined that could carry a physical object to JADES GS Z140 within any timescale meaningful to humanity or even to life on Earth. The distance is not a practical obstacle. It is a fundamental one. That galaxy exists in our universe, shares the same physical laws, is made of the same atoms, and yet it is as unreachable as if it existed in a different reality entirely. That thought carries with it a very particular kind of loneliness. Not a painful loneliness, but a cosmic one. The loneliness of knowing that the universe is almost entirely beyond our grasp, and that we have somehow found the curiosity and the ingenuity to look at it anyway. I want you to think about the ground beneath you right now. Whatever surface you're resting on, whether it is a bed, a couch, a floor, ultimately connects downward through layers of material that eventually reach the bedrock of the Earth itself. That rock is old. Some of the oldest exposed rock formations on Earth date back roughly 4 billion years. The Earth itself, as a planetary body, formed approximately 4.5 billion years ago from a rotating disk of gas and dust surrounding a young star that we now call the Sun. Everything you have ever touched, every landscape you have ever seen, every ocean and mountain and grain of sand is part of a world that assembled itself from cosmic debris roughly 4.5 billion years ago. That number feels ancient from a human perspective, and it is ancient. But tonight, I need you to hold it alongside another number. The light from JADES GS Z140 left its source 13.4 billion years ago, which means that when that light began its journey across the universe, our planet did not exist. Not yet. Not even close. The Sun had not formed yet either. Our solar system, including every planet, moon, asteroid and comet that orbits our star, assembled itself roughly 4.5 billion years ago from the remnants of earlier stellar generations. Those earlier stars, which lived and died before our Sun was born, forged the heavier elements in their cores through nuclear fusion and scattered them into space when they exploded as supernovae. The carbon in your body, the oxygen in the air you breathe, the iron in your blood, all of it was manufactured inside stars that lived and died before our Sun existed. And when that ancient light from JADES GS Z140 began its journey, even those earlier stellar generations had barely begun their lives. The raw materials from which our solar system would eventually be assembled were still locked inside stars that had only recently switched on for the very first time. Our entire cosmic lineage, every star that contributed to our existence, was still in its earliest infancy when this light departed. Hold that thought and extend it a little further. Life on Earth has existed for roughly 3.8 billion years, beginning as simple single-celled organisms in the early oceans of a young planet. Complex multicellular life did not appear until roughly 600 million years ago. Animals with skeletons appeared about 500 million years ago. Dinosaurs walked the Earth from roughly 240 million years ago until their extinction 66 million years ago. Our own genus, Homo, appeared perhaps 2 to 3 million years ago. Modern humans, Homo sapiens, have existed for roughly 300,000 years. All of that, the entire pageant of life on Earth from its chemical beginnings in ancient seas to every creature that has ever lived and died on this planet, fits inside a time span that began 9 billion years after this light departed its galaxy. By the time the first living cells appeared on Earth, this light had already been travelling for nearly 10 billion years. It was more than halfway through its journey before life on our world had even begun. There is something in this timeline that I find simultaneously humbling and quietly magnificent. We tend to think of ourselves as ancient when we look at human history. A civilization that built pyramids 4,000 years ago feels remote and inaccessible to us. A species that walked upright 2 million years ago seems almost impossibly distant from the present, and yet all of that recedes to nothing when placed against the age of this light. Every ancestor you have ever had, every human being who ever lived, every creature in your entire evolutionary lineage back to the first self-replicating molecule in a warm early ocean, every second of their collective existence fits inside a sliver of time that this light spent crossing the void before our world was born. We are newcomers. We are extraordinarily, almost absurdly new. But here is what makes that fact not depressing but astonishing. That light, which left its source before the atoms of our world had assembled, before life had a chance to begin its long experiment on this small planet, before any of the hundreds of millions of species that have ever existed here had yet evolved, that light crossed the universe and arrived at precisely the right moment. It arrived after we had developed the scientific understanding to recognize what it was, after we had built the mathematics to calculate its redshift, after we had launched into space and deployed the instruments capable of detecting it, after we had developed the theoretical framework to understand what its existence implies about the history of the cosmos. A few decades earlier, and we could not have seen it. A few decades earlier, and we lacked the tools. The timing of this encounter between ancient light and curious minds is itself something worth sitting with quietly in the dark. Think about what the universe looked like when this light departed. The galaxy that emitted it was a young, chaotic, intensely active structure, blazing in an early cosmos still thick with gas and newly forming stars. Surrounding it in every direction was a universe still in the process of clearing the fog of its youth, still filling with the first light from the first stellar generations, still assembling the large-scale structure of galaxy clusters and cosmic filaments that we see today. There were no planets like Earth anywhere in the universe when this light left. The heavy elements needed to build rocky planets had barely begun to be forged. Silicon, iron, calcium, phosphorus. The building blocks of geology and biology alike were still being manufactured inside the first massive stars, waiting to be scattered by their deaths into the gas clouds from which later generations of stars and their planets would form. When I sit with that timeline, I feel something that is difficult to name precisely. It is not quite sadness and not quite joy. It is something closer to a profound sense of perspective. Everything we worry about, every deadline and disappointment and conflict and fear that fills the texture of daily human life, exists within a thin film of time sitting atop an almost incomprehensible depth of cosmic history. The light now sitting in our databases, reduced to numbers and graphs and scientific papers, carries within it information from a time so remote that our existence was not even a possibility when it was emitted. We were not a twinkle in the eye of the cosmos. We were not a future event on any conceivable horizon. We were simply not part of the picture at all, and yet we received the light. We caught it. We measured it. We understood, at least partially, what it was telling us. That act of reception and comprehension, a species of 300,000-year-old beings on a 4.5 billion-year-old planet in a 13.8 billion-year-old universe, reaching out and touching the edge of everything, is perhaps the most remarkable thing I know of. The light did not know it would be received. It was simply travelling, as light does, indifferent to what lay in its path. It was we who decided to look. It was we who built the instruments, planned the surveys, processed the data, and recognized what we had found. In a universe that seems mostly to proceed without witnesses, we are the witnesses. And tonight, we are witnessing together. Science is, at its core, a system for being surprised. You build a model of how things work. You make predictions based on that model. You gather observations and check whether the predictions hold. Most of the time, in mature fields, they do. The model survives. Your confidence in it grows. But occasionally, and these are the moments that define the history of science, an observation arrives that does not fit, that sits outside the boundaries of what the model allows, that forces you to confront the uncomfortable possibility that something you believed with great confidence might be incomplete, or wrong, or missing something fundamental. JADES GSZ 14-0 is one of those observations. It is not just the most distant object ever found. It is an object that, according to our best understanding of how the early universe works, should not look the way it looks. To understand why, you need to understand what our models predicted we would find when we looked this far back in time. For decades, cosmologists have been refining a theoretical framework called the Lambda Cold Dark Matter model, often shortened to Lambda CDM. It is the standard model of cosmology, the best description we have of how the universe began, evolved, and formed the structures we see today. Among other things, this model makes specific predictions about how galaxies form and grow in the early universe. According to Lambda CDM, galaxy formation is a hierarchical process. Small structures form first. Dark matter clumps together into halos, and ordinary matter falls into those halos, forming small, dim proto-galaxies. Over time, these small structures merge with each other, gradually assembling larger and larger galaxies through a slow process of cosmic construction. The early universe in this picture should be populated mainly by small, faint, young, irregular proto-galaxies still in the earlier stages of assembly. Massive, well-developed galaxies should not yet exist in any significant numbers. What Webb found instead, in object after object at extreme redshifts, was something different. Galaxies that were brighter than expected. Galaxies that were more massive than expected. Galaxies that appeared to have been forming stars at extraordinary rates for longer than our models said they should have had time to do. And JADIS GSZ 14-0, sitting at the extreme end of this trend, is the most dramatic example yet. When astronomers analysed the spectroscopic data from this galaxy, they found that it was shining with the light of roughly 500 million solar masses worth of stars. 500 million times the mass of our Sun, already assembled into stars at a time when the universe was only 290 million years old. Under the Standard Model, building that much stellar mass in that shorter time is not just unlikely. It is extraordinarily difficult to explain. Here is the thing most people do not realise about the timescales involved. 290 million years sounds like a long time by human standards. It is longer than the age of the dinosaurs, but in cosmic terms it is almost nothing. Stars do not form instantaneously. They condense from clouds of gas over millions of years. They live for millions or billions of years before dying. Building a galaxy with hundreds of millions of solar masses of stars requires not just the raw material, but the time to go through multiple cycles of star formation, stellar evolution, and the complex feedback processes by which galaxies regulate their own growth. Under our standard models, the universe at 290 million years old simply had not had enough time to assemble all of that stellar mass in one place. The construction timeline does not work. It is like arriving at a building site on the morning of the first day and finding a skyscraper already standing. But the surprises do not end with the mass. The spectroscopic analysis of JADIS GSZ 14-0 revealed something else that deepened the puzzle considerably. The light from this galaxy showed the chemical signatures of elements heavier than hydrogen and helium. Oxygen, in particular, was detected. In the language of astronomy, any element heavier than hydrogen and helium is called a metal, regardless of whether it would be considered a metal in everyday life. The presence of oxygen in this galaxy's spectrum means that stars in this galaxy had already lived, burned through their fuel, and died, scattering their heavier elements back into the surrounding gas, which then enriched the next generation of stars. This cycle of stellar birth, death, and chemical enrichment takes time. Multiple generations of stars had already come and gone inside this galaxy before the light we detected was even emitted. That, in the context of a universe only 290 million years old, is deeply, genuinely startling. The scientific community's response to these findings has been a combination of excitement and serious theoretical concern. Some researchers have proposed that our standard models of galaxy formation need to be revised to allow for faster and more efficient star formation in the very early universe than previously assumed. Perhaps the conditions of the early cosmos, denser gas, different dark matter distributions, higher rates of gas infall into early halos, allowed star formation to proceed much more rapidly than our models suggest. Others have proposed that the initial mass function of stars in the early universe, the distribution of stellar masses at birth, was weighted toward more massive stars than we see forming today. Massive stars live short, brilliant lives and produce heavier elements quickly, which could explain the chemical enrichment seen in JADIS GSZ 14-0 in a relatively short time frame. Still others have suggested more radical possibilities. Some researchers have raised the question of whether exotic physics might be at play in the very early universe. Whether the role of dark matter, or the initial conditions of the Big Bang itself, or even certain assumptions built into our standard cosmological model, might need to be reconsidered in light of what Webb is finding. These are serious proposals from serious scientists, not fringe speculation. When observational data consistently conflicts with theoretical predictions across multiple independent observations, the scientific response is to take that conflict seriously and ask what it is telling us. The data from Webb's deep field surveys is doing exactly that, telling us insistently and repeatedly that something in our picture of the early universe may need revision. What I find most compelling about this puzzle is not the technical details of the solution, whatever it turns out to be. It is what the puzzle itself represents. We built the most powerful telescope in human history and pointed it at the furthest reaches of space and time, fully expecting to confirm what we already believed. And instead of confirmation, we got a challenge. We got the universe refusing to behave exactly as predicted. We got, in the most literal sense, a surprise. And in science, surprises are not setbacks. They are invitations. Invitations to look more carefully, think more deeply, and ultimately understand more completely. The galaxy that should not exist is not a problem to be embarrassed about. It is a door, and somewhere on the other side of it is a more accurate, more nuanced, more complete picture of how the universe made everything, including us. There is a question that I suspect has been forming quietly in the back of your mind as we have travelled through this story together. A natural question, the kind that arises almost inevitably once you sit with the idea of looking at something 13.4 billion light-years away. If that light has been travelling for all that time, if it left its source when the universe was barely 290 million years old, then where is that galaxy now? What happened to it over the billions of years since that snapshot was taken? And where does it sit in the universe today? Not where it was when the light departed, but where it actually is at this moment as you lie here listening in the dark. The answers to those questions are, in their own way, just as strange and just as humbling as everything else we have discussed tonight. To understand the answer, you need to remember something we touched on earlier in our journey. The universe is expanding. Not expanding into anything, not like a balloon inflating inside a larger room, but expanding in the sense that the space between things is stretching. Every region of space is growing, very slightly, every moment. Over small distances and short timescales, this expansion is negligible. You do not notice the space between you and your walls growing, because it is not growing at any rate that matters on human scales. But over cosmic distances and cosmic timescales, the expansion of space becomes the dominant fact about the universe. Galaxies are not flying through space away from us. The space between us and them is growing, carrying them with it. The way dots on the surface of an inflating balloon move apart from each other, not because they are swimming across the rubber, but because the rubber itself is stretching. Now apply that to JADIS GSZ 14-0. When the light we detected left that galaxy, it was at a certain distance from what would eventually become our corner of the universe. Let us call that the emission distance. Over the 13.4 billion years that the light was travelling toward us, space continued to expand. The galaxy itself was being carried further and further away by that expansion, even as its ancient light was crossing the void in our direction. So by the time that light finally arrived at Webb's mirror, the galaxy that emitted it had already moved considerably further away than the light travel distance alone would suggest. The actual current distance to JADIS GSZ 14-0, accounting for all of that expansion, is estimated at approximately 33 to 35 billion light-years. Not 13.4 billion, 33 to 35 billion. The galaxy is more than twice as far away right now as the light travel time alone would imply. And it is moving further away every moment. The expansion of space means that the distance between us and this galaxy is growing continuously. Moreover, because of a phenomenon called accelerating expansion, driven by what cosmologists call dark energy, the rate at which the most distant galaxies are receding from us is itself increasing over time. The galaxy is not just moving away, it is moving away faster and faster. At the distances involved with JADIS GSZ 14-0, the recession speed due to cosmic expansion is already many times the speed of light. This does not violate Einstein's special relativity, which prohibits objects from moving through space faster than light. It is space itself that is expanding, and space has no such speed limit. But the practical consequence is total and absolute. No signal we could ever send, no matter how fast, no matter what future technology might achieve, could ever catch up with this galaxy. It has already passed beyond any conceivable reach. That fact carries with it a very particular quality of finality. We have found this object. We have measured it. We have studied its light and extracted from it remarkable information about the early universe, and yet we will never know what it is today. We cannot observe it as it currently exists, because the light showing us its current state will not arrive here for tens of billions of years if it arrives at all. And in the far future, as the expansion of space accelerates, even that future light may never reach us. The galaxy we found at the edge of everything exists, right now, somewhere in the cosmos, almost certainly evolved beyond recognition from the young blazing structure we detected. It may have grown into a massive elliptical galaxy containing trillions of stars. It may have merged with dozens of neighbouring galaxies over the course of billions of years. It may have developed a supermassive black hole at its centre that dwarfs anything in our own cosmic neighbourhood. We will never know. That galaxy's current story is permanently inaccessible to us, sealed away behind the expanding barrier of space and time. Think about what that means for a moment. The most distant object we have ever found is also, in a very real sense, the most unknowable. We have a single ancient photograph of it, taken when it was an infant. We know nothing of its adolescence, its maturity, its current state. We received one faint signal from the beginning of its existence, and then silence. It is as if you found a single photograph of a person taken 2 days after their birth, and knew with certainty that you would never be able to find them again, never know who they became, never know what their life held. The photograph is precious precisely because it is all there is. Every measurement we have made of this galaxy is irreplaceable, not because we could not in principle point Webb at it again, but because what we are seeing is a moment frozen in the deep past that cannot be revisited or updated. And yet, knowing where that galaxy is now, or more precisely knowing that it is at a distance of 33 to 35 billion light-years and receding at superluminal speeds due to cosmic expansion, does tell us something profound about the scale of the universe we inhabit. It tells us that the observable universe, our bubble of knowable space, is not the universe. It is a small, finite, precious window onto something vastly larger. The galaxies we can see are not all the galaxies there are. They are simply the ones close enough that their ancient light has had time to reach us. Beyond our horizon, in every direction, there are almost certainly more galaxies, more stars, more worlds, more of everything. Some of those regions were already receding from us faster than light at the moment of the Big Bang, and have never been in causal contact with us at all. They are part of the same universe, governed by the same physics, but forever beyond any possible communication or observation. Where is that galaxy now? It is out there, impossibly far away, moving further with every passing second, utterly beyond reach. It exists in the same universe as you and I, shaped by the same laws, made of the same fundamental particles, and it is as remote as if it existed in a dream. I find something deeply moving in that. Not tragic exactly, more like the feeling of looking at a light on the horizon of the sea and knowing it comes from a ship you will never meet. The light is real. The ship is real. The distance between you is also real. And somehow, the fact of that unreachable light makes the night feel both lonelier and more full than it did before. There is a question that has haunted astronomy for decades. A question so simple to state, and yet so difficult to answer, that it has generated more serious scientific speculation than almost any other puzzle in the field. The physicist Enrico Fermi is said to have asked it over lunch with colleagues in the summer of 1950, in a casual, almost offhand way that belied its enormous weight. If the universe is so vast and so old, and if the conditions for life and intelligence seem to arise naturally from the same physical processes that built galaxies and stars and planets, then where is everybody? Where are the signs of other civilizations? Where are the radio signals, the megastructures, the deliberate transmissions, the accidental leakage of technology into the cosmos that a sufficiently advanced civilization would inevitably produce? We have been listening in various ways for decades, and the answer we have received is the same every time. Silence. Complete, unbroken, deeply unsettling silence. This silence has a name, the Fermi paradox. And while it is traditionally discussed in terms of our own Milky Way galaxy, the discovery of JD's GSZ 14-0 adds a new and particularly striking dimension to it. Here is why. This galaxy formed in the first few 100 million years of cosmic history. It already contained hundreds of millions of solar masses of stars when the universe was less than 300 million years old. If even a fraction of those stars had planets, and our observations of planetary systems around nearby stars strongly suggest that planets are extraordinarily common, then some of those planets had a head start on the history of life of nearly 13.5 billion years compared to Earth. 13.5 billion years is an almost incomprehensible advantage. Our entire evolutionary history, from the first self-replicating molecules to the civilization listening to this right now, took only about 3.8 billion years. A civilization in Jadiz GSZ 14-0 could have run that experiment more than 3 times over before our sun had even formed. Let that sink in slowly. If life arises with any reasonable probability given the right conditions, and if intelligence eventually emerges from that life with any reasonable probability given enough time, then some of those early galaxies, those young blazing structures we are now detecting at the edge of the observable universe, may have contained civilizations billions of years ago. Civilizations that had billions of years to develop, to expand, to modify their environment in ways that might be detectable across cosmic distances, and yet we detect nothing. No anomalous signals, no engineered structures, no pattern in the noise that suggests deliberate communication or the byproduct of truly advanced technology. The universe, as far as every instrument we have pointed at it can determine, is silent. And the older we realize the cosmos is, and the earlier we find galaxies capable of hosting life, the more profound that silence becomes. There are many proposed explanations for the Fermi paradox, and scientists and philosophers have been generating them for decades with impressive creativity. Perhaps life is extraordinarily rare, and despite the vastness of the cosmos and the billions of years available, we are simply one of only a handful of civilizations that have ever arisen anywhere. Perhaps intelligence is common, but technological civilization is not, and the leap from biological intelligence to the kind of civilization that reshapes its environment and broadcasts its presence is far more difficult than it appears. Perhaps civilizations reliably destroy themselves before they reach the stage of interstellar communication through war or environmental collapse or the development of technologies they cannot control. These explanations are sometimes called the Great Filter, the idea that somewhere in the chain from simple chemistry to spacefaring civilization, there is a barrier that almost nothing gets through. The terrifying version of the Great Filter is this: if the filter is behind us, if the hard step was something in our past, perhaps the origin of life itself, or the development of the eukaryotic cell, or the emergence of multicellular organisms, then we may be among the rare survivors who made it through. The future could be open. But if the filter is ahead of us, if civilizations routinely reach our level of development and then reliably fail to proceed further, then the silence of the cosmos is not reassuring. It is a warning. It is the statistical signature of something that waits for civilizations at a certain stage and ends them before they can become detectable. No radio signals, no signs of engineering, no evidence of anyone out there having made it through. The silence would then be the loudest possible alarm, and we would be standing just before whatever causes it. I want to be careful here, because this territory sits at the boundary of science and speculation, and I do not want to overstate what the evidence actually tells us. The Fermi paradox is a genuine scientific puzzle, but it does not have a confirmed answer. The silence could simply reflect the difficulty of detecting signals across the kinds of distances involved, even within our own galaxy. A civilization broadcasting radio waves from the other side of the Milky Way might be undetectable to our current instruments, even if they were transmitting continuously. The universe is also extraordinarily large, and our search, while serious and ongoing, has covered only a tiny fraction of the relevant parameter space. The absence of evidence is not evidence of absence, as the saying goes, though it does become more suggestive the longer and more thoroughly the search continues without a result. What I find most haunting about connecting the Fermi paradox to the most distant objects we have ever found is this: those early galaxies, blazing in the first few 100 million years of cosmic history, had the raw ingredients for everything: stars, elements, time, the same physics that eventually produced us. And if life and intelligence are natural outcomes of those ingredients given enough time, then the universe should be, by now, extraordinarily full of awareness. After 13.8 billion years of stellar evolution, planetary formation, chemical complexity and biological possibility, the cosmos should be thick with minds. And yet from where we stand, it appears empty. One pale blue dot of confirmed awareness, surrounded by an ocean of silence so deep and so vast that even our most powerful instruments cannot find a ripple in it that suggests we're not alone. Maybe the silence means we're special. Maybe it means we're early, arriving at the party of cosmic awareness before most other guests. Maybe it means something darker. Tonight, I cannot tell you which of those possibilities is true. Nobody can yet, but I can tell you that looking at Jade's GSC 14-0, knowing that its ancient light implies a universe old enough and large enough to have generated awareness billions of years ago, and then looking back at our instruments and hearing nothing, is one of the most profoundly strange and quietly terrifying experiences that modern astronomy offers. The silence beyond the edge is not empty. It is full of a question that we have not yet found the answer to. And tonight, lying in the dark, you are as close to the edge of that question as any human being has ever been. We have spent a great deal of tonight looking outward, pushing our gaze further and further from the comfortable familiarity of our own solar system, past the stars of our galaxy, past the neighbouring galaxies of our local group, past billions of light years of cosmic structure, all the way to the edge of the observable universe and the most distant object human science has ever detected. But there is a question lurking behind everything we have discussed that I want to bring into the open now. A question that is, in its own way, even more vertiginous than anything we have yet considered. What lies beyond the edge? Beyond the cosmic horizon that defines the limits of our observable universe? Beyond the point from which light has had time to reach us? Beyond the boundary at which our instruments fall permanently silent? What is actually there? The first thing to understand is that the edge of the observable universe is not the edge of the universe itself. This is a distinction that sounds simple, but carries enormous implications. Our cosmic horizon is defined by our location and by the age of the universe. It is the boundary of what we can see from here, not the boundary of what exists. Beyond our horizon, space almost certainly continues. The universe does not simply stop where our vision stops. There is no wall, no void, no sudden end to the fabric of space and time at the point where our most powerful telescopes run out of light to collect. The horizon is our horizon. It is a feature of our perspective, not a feature of physical reality. And beyond it, the overwhelming consensus among cosmologists is that more universe continues, structured by the same laws of physics, filled with the same kinds of matter and energy, extending in the same expanding fabric of space that we inhabit here. How much more? This is where the answer becomes almost impossible to hold in the mind. Current measurements of the geometry of the universe suggest that it is, on the larger scales, very close to flat. In cosmology, flatness is a technical term describing the overall curvature of space. A flat universe is one in which the geometry of space on the larger scales obeys the familiar rules of Euclidean geometry, where parallel lines never meet, and the angles of a triangle always add up to 180 degrees. The significance of this measurement is profound. A spatially flat universe, according to our best theoretical understanding, is almost certainly infinite in extent. Not very large, not unimaginably large, infinite, extending without limit in every direction, filled with matter and energy and structure, forever. If that is correct, then our observable universe, with its 46 billion light-year radius and its 2 trillion galaxies, is an infinitesimally small sample of a whole that has no boundary and no end. Pause with that for a moment. An infinite universe means that everything that can happen, given the laws of physics and the initial conditions of the Big Bang, does happen. Somewhere. In an infinite universe, every possible arrangement of matter and energy that is consistent with physical law is realized. Not once, but infinitely many times. There are, if this picture is correct, infinitely many regions of the universe that look exactly like our observable universe. Infinitely many regions that are almost identical to ours but with small differences. Infinitely many versions of every possible cosmic history. This is not science fiction. It is a straightforward mathematical consequence of infinite space combined with the uniform distribution of matter that our observations support. Cosmologists call this the Level 1 multiverse, and it requires no exotic new physics, no parallel dimensions, no speculation beyond what our best current measurements already imply. But the story does not end there. The dominant theory of the very early universe, called cosmic inflation, proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid that regions of space were driven apart faster than light could connect them. Inflation elegantly explains several features of the universe that would otherwise be deeply puzzling, including its flatness, its uniformity on large scales, and the specific pattern of tiny fluctuations in the cosmic microwave background that we can measure with extraordinary precision. But inflation also makes a remarkable prediction. In most versions of the theory, inflation does not end everywhere at once. It ends in some regions, creating what we might call bubble universes, while continuing to inflate in others. New bubbles constantly nucleate and expand within the still inflating background. The result is an eternal self-reproducing cosmos of bubble universes, each one a vast space with its own post-inflation history, potentially with its own physical constants, its own particle physics, its own rules about how matter and energy behave. This is what cosmologists call eternal inflation, and it is one of the most seriously discussed ideas in modern theoretical physics. It is not a certainty. It is not directly observable, essentially by definition, since the other bubble universes, if they exist, are separated from ours by regions of still inflating space that light could never cross. But it emerges naturally from the same inflationary framework that so successfully explains what we can observe. And if it is correct, then our entire observable universe, with its hundreds of billions of galaxies and its 13.8 billion years of cosmic history, is a single bubble in an ocean of bubbles, most of which we can never detect, never communicate with, never know. The most distant object we have ever found is not near the edge of everything. It is simply near the edge of our particular window, onto a reality that extends beyond any horizon we could ever reach. Here is the thing most people do not realize when they first encounter these ideas. They are not the product of unbounded speculation, or the wishful thinking of theorists who prefer a large universe to a small one. They emerge from careful, mathematically rigorous extensions of the same theoretical framework that makes extraordinarily precise predictions about the observable universe and has been confirmed by decades of observation. The same inflationary theory that predicts the spectrum of fluctuations in the cosmic microwave background with stunning accuracy also predicts eternal inflation. You cannot easily accept one without taking the other seriously. The universe beyond our horizon is not a fantasy. It is the logical continuation of the physics we observe here, extended to scales we cannot directly probe. And this brings me to something I want you to carry with you as you settle deeper into the quiet of tonight. We found the most distant object ever detected. We measured its light. We understood, at least partially, what it was telling us. And in doing so, we did not reach the edge of the universe. We reached the edge of our knowledge. We reached the boundary not of space itself, but of what our position in space and our moment in time allow us to see. Beyond that boundary, the universe continues. It continues in ways we cannot directly observe, in scales we cannot directly measure, with a fullness that makes even the sweep of everything we have discussed tonight seem intimate by comparison. We are not at the centre of a small universe. We are at the edge of our view into an enormity that has no known limit. And there is something in that, something in the combination of our smallness and our curiosity, that I find not terrifying at all. I find it quietly, profoundly magnificent. Every record in the history of astronomy has been broken. Every boundary that seemed like the final frontier turned out to be a temporary one, a line drawn by the limits of the instruments available at the time, rather than by the limits of the universe itself. The first quasars discovered in the 1960s seemed impossibly distant, and then more distant ones were found. The first galaxies detected beyond redshift 5 seemed unreachably ancient, and then surveys pushed to 6, 7, 8, and beyond. When the Hubble Space Telescope produced its deep field images in the mid-90s and revealed galaxies at distances that had seemed almost theoretical, the response from the scientific community was not satisfaction but hunger, not arrival but anticipation. Because every expansion of the frontier reveals not just what is there but also a glimpse of what might lie just beyond the new edge, and right now, as the James Webb Space Telescope continues its methodical, patient survey of the deep universe, that hunger is very much alive. JAID's GSZ 140 currently holds the confirmed spectroscopic record for the most distant object ever observed, a redshift of 14.32, corresponding to a universe 290 million years old. That number is extraordinary. It represents the absolute frontier of human observational reach, and it is almost certainly not the final record. The JAID survey is ongoing. Webb continues to operate. Data continues to accumulate, and buried somewhere in the infrared glow of the deep universe, almost certainly waiting to be found, are objects at even higher redshifts, objects whose light left their sources even earlier in cosmic history, even closer to the moment when the very first structures in the universe were switching on for the first time. The next record breaker may already exist in Webb's data, waiting for the right analysis to pull it from the noise. To understand how astronomers will find the next record breaker, it helps to understand what they are actually looking for. The process begins with deep imaging surveys, in which Webb stares at carefully chosen patches of sky for many hours or even days of accumulated exposure time, building up enough light to detect objects far too faint to see in shorter observations. In these deep images, astronomers look for objects that display the Lyman break signature we discussed earlier, that sharp cut-off in brightness at a specific wavelength that indicates extreme distance and high redshift. Candidate high redshift objects are then prioritized for follow-up spectroscopic observation, which provides the definitive confirmation of redshift by spreading the object's light into its full spectrum and measuring the precise wavelengths of known spectral features. This two-step process of imaging identification followed by spectroscopic confirmation is how every distance record has been broken, and it is how the next one will be broken too. The practical challenge is formidable. As redshift increases, the objects being sought become fainter, and their light shifts to longer and longer infrared wavelengths. At a redshift of around 15 or 16, which would correspond to a universe only about 220 or 200 million years old, the Lyman break shifts to wavelengths near the edge of Webb's sensitivity range. Beyond that, into the realm of redshifts above 20, if such objects exist and are luminous enough to detect, we would need instruments capable of reaching wavelengths even further into the infrared, beyond what Webb was designed to cover efficiently. Future space telescopes, currently in various stages of planning and proposal, are being designed with exactly this goal in mind, to push past Webb's frontier and into the very earliest epochs of cosmic history. But for now, Webb still has significant unexplored territory within its reach, and the scientific community is actively mining it. What do astronomers expect to find as they push closer to the absolute limit? The theoretical target that drives much of the excitement in this field is called the epoch of Rayonization, and more tantalizing still, the very first stars, which astronomers call population 3 stars. These hypothetical objects, never yet directly detected, are believed to have been the first stars ever to form in the universe, condensing from pure primordial hydrogen and helium with no heavier elements at all. Population 3 stars were almost certainly extremely massive, perhaps hundreds of times more massive than our Sun, and they burned with ferocious intensity for only a few million years before exploding as supernovae and seeding the early cosmos with the first heavy elements ever created. Detecting these stars directly, or detecting the signatures of their explosions, is one of the grand observational goals of modern astrophysics. Webb may be sensitive enough to catch the brightest of these events if they are associated with sufficiently luminous host galaxies or explosion signatures. Beyond population 3 stars lies the ultimate observational goal, the cosmic dawn itself. The moment when the universe first became luminous, when the first sources of light switched on in the post-Dark Ages cosmos, and began the long process of Rayonizing the surrounding hydrogen gas. This transition from darkness to first light happened somewhere in the range of redshifts between 15 and 30, corresponding to a universe between 100 and 250 million years old. Precisely when it happened, how it happened, and what the very first sources of light looked like are among the most actively debated questions in cosmology. Every new high redshift object discovered by Webb brings us one small step closer to answering those questions. Every record-breaking discovery is not just a milestone but a probe, a sample drawn from an era we have never been able to directly observe before. There is something I find genuinely moving about the ongoing nature of this search. The record will break again. Perhaps it will break while you are asleep tonight, data already sitting on a server somewhere waiting to be fully analysed. Perhaps it will break next month or next year or in 5 years, when a new observational campaign produces an object at redshift 15 or 16 that shatters the current frontier. But it will break. The history of this field admits no other reasonable expectation, and when it does, the response in the astronomical community will be the same it has always been. Not a sense of completion, not a feeling that the final answer has been reached, but a renewed excitement, a recalibration of models and expectations, and an immediate, irresistible impulse to ask what lies just beyond the new record. That impulse, that insatiable reaching toward the next horizon, is one of the most distinctly human things I know. Other animals perceive the world around them with extraordinary acuity. They navigate, hunt, communicate, and solve problems with remarkable sophistication. But the desire to look beyond the visible horizon, to ask what lies further than the eye can see, to build instruments that extend perception into realms that natural senses cannot reach, and then to be immediately hungry for what lies beyond those instruments in turn, that seems to be something particular to us. It has driven us from the first person who climbed a hill to see further than they could from the valley floor, all the way to the teams of engineers and scientists who devoted decades of their working lives to placing a gold-plated hexagonal mirror in space and teaching it to catch the oldest light in the observable universe. The record will break again, and we will break it, because that is what we do. We have travelled a long way tonight, from the quiet act of looking up at the stars above your head, through the history of the instruments we built to see further, through the discovery of the most distant object ever found, through the existential vertigo of its distance and age, through the silence of the cosmos and the mysteries that silence implies, through the infinite reach of what lies beyond our horizon, and through the ongoing human drive to push the frontier further still. And now, before we rest, I want to try to say something true about all of it. Not a summary of facts, but something closer to what all of these facts taken together actually mean. Because I think there is a truth sitting at the centre of everything we have discussed tonight that is simultaneously the most terrifying and the most beautiful thing I know how to say. Here is the terrifying part first. The universe is almost entirely beyond our reach, almost entirely beyond our knowledge, almost entirely indifferent to our existence. JD's GS Z140, the most distant object we have ever found, is so far away that no physical object, no signal, no influence of any kind could ever connect us to it again. The light we caught from it is a one-way message, sent before our world existed, received by instruments we barely had time to build, before the expansion of space made even that faint signal harder to catch. Beyond that galaxy, our horizon continues, and beyond our horizon, the universe extends in all likelihood without limit, filled with structures and events, and possibly even minds that we will never know existed. The fraction of the universe we can ever observe, study, or interact with is so close to zero that it is effectively zero. We are sealed inside our tiny bubble of knowable space, pressing our faces against the glass and seeing, at best, the faintest outline of what lies on the other side. And the physics of our situation is not going to improve with time. Because of the accelerating expansion of the universe driven by dark energy, the cosmic horizon is effectively shrinking relative to the total universe. Galaxies that are currently just within our observational reach are being carried away from us at speeds that will eventually make them permanently unreachable. In the far future, a civilization in our galaxy, if one still exists, will look out at a universe that appears nearly empty. All the distant galaxies we can currently see will have been carried beyond the horizon by the relentless expansion of space. The night sky will contain only the stars and galaxies of our own local group, the small cluster of galaxies gravitationally bound to the Milky Way and Andromeda, which will by then have merged into a single large galaxy. Everything else will be gone, not destroyed but simply unreachable, swept beyond the horizon of light and time. We live at what may be the best moment in all of cosmic history for observing the universe in its full glorious extent, and even now, even at this optimal moment, what we can see is almost nothing compared to what exists. That is the terrifying part. Here is where the beautiful part begins. We saw it anyway. We, a species that appeared in the last few 100,000 years of a 13.8 billion-year-old universe, on a small rocky planet orbiting an unremarkable star in the outer spiral arm of one of hundreds of billions of galaxies, somehow found the curiosity, the mathematical insight, the engineering capability, and the collective determination to build an instrument sensitive enough to catch light that has been travelling for more than 13 billion years, and to extract from that impossibly faint signal real, meaningful, scientifically rigorous information about the universe in its infancy. That is not a small thing. That is, by any measure I can apply to it, one of the most extraordinary things that has ever happened in the history of the cosmos. Think about the chain of events that had to occur, The Big Bang had to produce precisely the right ratio of matter to antimatter to leave any matter at all. The laws of physics had to be calibrated to allow stars to form and burn and die and scatter heavy elements into the cosmos. Those elements had to condense into a second or third generation star with a stable planetary system. One of those planets had to develop liquid water and the chemistry of life. Life had to survive mass extinctions and the slow catastrophes of geological time. Intelligence had to emerge from that life. Language had to develop, then writing, then mathematics, then science, then the specific branch of science that asks questions about the structure and history of the cosmos. Telescopes had to be invented, then refined, then launched into space. The particular sequence of funding decisions and engineering breakthroughs and international collaborations that produced the James Webb Space Telescope had to succeed. And then, finally, astronomers had to point that telescope at the right patch of sky for the right amount of time and have the analytical tools to recognize what they were seeing. Every single step in that chain had to work, and it did. Here is the thing most people do not fully sit with when they learn about the scale of the universe. The fact that we exist, that we are aware, that we are curious, that we ask questions about things so far removed from any immediate survival need as the distance to the most ancient galaxy ever observed, is itself a cosmic phenomenon. We are not observers standing outside the universe looking in. We are part of the universe. We are the universe, organizing itself into structures complex enough to wonder about its own origins. Every atom in your body was forged inside a star. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was manufactured in stellar furnaces and scattered by stellar deaths across billions of years of cosmic history before assembling, through an improbably long chain of events, into the arrangement that is you, lying here tonight, thinking about the most distant galaxy ever found. You're not separate from what we have been discussing. You are made of it. The terrifying and beautiful truth is this. The universe is almost entirely dark, almost entirely empty by volume, almost entirely silent, almost entirely beyond reach. It is governed by physical laws that have no interest in our comfort or our survival, or our longing to understand. It is staggeringly old and staggeringly vast and almost entirely indifferent. And somewhere in that darkness, on a small warm world orbiting a middle-aged star, something happened that may be among the rarest events in the cosmos. The universe became aware of itself. It developed eyes to see its own structure, minds to comprehend its own history, voices to speak its own name into the dark. We are those eyes. We are those minds. We are those voices. And tonight, together, we looked further than we have ever looked before and caught a glimpse of something that was blazing in the darkness before we were even possible. The terror and the beauty are not in opposition. They are the same thing. Seen from far enough away, they always are. We have reached the end of our journey tonight, and I want to take a moment before we part to simply be here, in this quiet, at the edge of everything we have seen together. You have travelled further tonight than any human being travelled for most of history, even in imagination. You have stood at the boundary of the observable universe and looked back across 13.4 billion years of cosmic time. You have visited a galaxy that existed before our world was born, before the atoms of your body had been forged, before any of the long chain of stellar generations that eventually produced us had even begun. And you have done all of this without leaving the warmth and darkness of wherever you are resting right now. That is not nothing. That is, in fact, something quietly extraordinary. I want to leave you with a few thoughts to carry into sleep. Not heavy thoughts, not the kind that keep you awake turning over unanswerable questions, but the kind that settle gently into the background of your awareness and change, very slightly, the texture of how the world feels when you open your eyes tomorrow. The first is this. The light from JADES GS Z14-0 travelled for more than 13 billion years to reach our instruments. It crossed an expanding universe, navigated the void between galaxies, survived intact through a journey of incomprehensible length, and arrived at precisely the moment when a species existed that was curious enough to look for it and capable enough to find it. There is something in that timing that I cannot quite explain and cannot quite dismiss. The universe sent a message from its own infancy, and we were here to receive it. The second thought is about scale, and what it does to worry. I do not say this to minimize anything you carry with you in your daily life. The difficulties and griefs and anxieties of human existence are real, and they matter, and they deserve to be taken seriously. But there is a particular kind of relief that comes from sitting inside the true scale of the cosmos, even briefly, even imperfectly. The universe is 13.8 billion years old and roughly 93 billion light-years across in the observable portion alone, extending in all likelihood without limit beyond that. In that context, the weight of any single day becomes lighter, not because your life is small and therefore unimportant, but because the universe is so large that your life, this specific irreplaceable arrangement of matter and consciousness and experience, becomes something remarkable simply by existing at all. You are here, you are aware, you are asking questions about the edge of everything. That is an astonishing thing to be. The third thought is about darkness. Tonight the sky above you, whether you can see it or not, is full of ancient light. Photons that have been travelling for years, centuries, millennia, millions of years, are landing on your roof and your walls and your skin right now as you listen to this. The universe is constantly sending us its history, broadcasting it in every direction, pressing it into every surface. Most of it we cannot see without instruments, but it is there. The dark is not empty. It is full of signals from the past, full of the accumulated light of billions of galaxies spanning billions of years, all of it streaming silently through the night above wherever you are. When you close your eyes in a moment and let sleep come, you will be lying inside that quiet flood of ancient light. It has been travelling since before you existed, and it will continue after. For now, you are briefly in its path. Let that be a comfort rather than a vertigo. I want to say something directly to you now, not as a narrator describing the cosmos, but as a voice that has spent this long night in your company. You chose to spend these hours thinking about the largest questions, about distance and time and the first light of the universe and what it means that we can find it. That choice says something about you. It says that you are the kind of person who is not content to live entirely on the surface of things, who wants to understand not just what is immediately around them, but what lies beyond, what came before, what the whole vast context of existence actually looks like from the outside. That curiosity is not a small quality. It is, in my view, one of the finest things a human being can have. It is the same quality that drove the scientists who built the James Webb Space Telescope, who designed the JD survey, who spent their careers preparing to find exactly the kind of object that broke every previous record. Curiosity is what got us to the edge of everything, and it will take us further still. The universe, as we have seen tonight, is almost entirely beyond our reach. The most distant object ever found is receding from us at speeds we cannot follow, into a future we cannot observe, having lived a history we can only glimpse in a single ancient snapshot. Beyond it, our horizon continues, and beyond the horizon the universe extends without known limit. It is, in the most literal sense, too large to fully comprehend. And yet here we are, comprehending as much of it as we can, reaching as far as our instruments allow, asking questions that will not be fully answered in our lifetimes. We are small creatures doing an enormous thing. We are the universe noticing itself, wondering about itself, reaching toward its own edges with instruments made of glass and metal and mathematics and human determination. That is what we are. That is what you are, lying here in the dark at the edge of sleep, with the ancient light of the cosmos falling silently all around you. Thank you for joining me tonight. Thank you for making the journey all the way to the edge of everything and back. If this exploration moved something in you, if it gave you that particular feeling of quiet awe that the cosmos reliably produces when you let it in, I would be grateful if you took a moment to like this or subscribe. It is a simple thing, but it helps this channel reach more curious minds, more people who want to spend their nights thinking about the largest questions rather than the smallest worries. Every person who finds their way to these explorations is another mind turning toward the sky, and that matters more than I can easily say. So let your breathing slow now. Let the darkness around you become comfortable and deep. Let the questions we have asked tonight settle into the background, not as unresolved anxieties, but as open doors, things to return to, things to carry lightly into the days ahead. The next time you step outside on a clear night and look up at the sky, I hope you will feel it differently than you did before, not just as a ceiling of distant lights, but as a window into deep time, a window onto the history of everything. Those points of light are not decorations. They are messages, ancient and ongoing, from a universe that has been telling its own story since long before we were here to listen. We are, improbably and wonderfully, the part of the universe that finally learned to listen back. Sleep well tonight. Dream of ancient light and impossible distances and the quiet courage it takes to keep asking questions about a cosmos that is under no obligation to answer. And tomorrow, and every night after, keep looking up at the stars. Good night.